Daniel Schlepfer from Resi Applications, and I'm going to show you how to process Headwall Nano Hyperspec data with Applanix input IMU data. So after opening PARGE, you can import the data first with one of the import functions. For instance, here we take the Hyperspec option for Hyperspec Headwall. And there are 6 options here, some for older Hyperspec systems. Hyperspec 2 is with this special Applanix. Nano 1 to 5 are various variations of the Nano standard data formats. So we choose Hyperspec 2. With Hyperspec 2, we first select the input file. This should be something like not a frame index, it should be a image file, a raw image file. Maybe I take this one as an example as an input file. The INS file for this one should for Applanix data should be an SPET like that one. And the sync file has been found automatically. That's a frame index file. The field of view is set automatically, so change it if it's not appropriate. And the same applies for the coordinate system. So you can choose it automatically, like a default zone, or you could use a user-defined coordinate system and search for it, but I use the default here. Now if I'm doing the import, this will look like that. So data has been imported. So eventually it may be converted to band sequential NV file formats, and we can check if import was correct. So we can check control. Plot image area. So plot image area, auxiliary plot image area, that's normal way I control the output. You see the image has been imported and it makes a reasonable area with all the borders due to the motion of the sensor is visible. Furthermore, you need to get the digital elevation model. So I'm loading a digital elevation model which has been prepared before. This was a medium filtered digital elevation model, so sometimes you have to filter it. So I'm loading it. Maybe you can have a look at this. So if you look at the DEM, that's a digital surface model of this area. So these are buildings, and there are some holes in there, so some filtering is really required for this kind of surface model. And maybe some more preparation would be required to get rid of certain artifacts. In this roof, you see there are some artifacts in the surface model. So this may need more elaboration to get a really good surface model to work with. But to start with, that's fine. Now we got everything prepared, and we could go directly to the processor. So I'll do a direct processing. To check it out, I'm gonna do a default RGB first, so it will only use 3 bands to process. And if you want to do a boresighting, for instance, you can do this on 3 bands only, so you don't need to process all 270 bands at first. This is only required in the final processing if you got the boresighting done correctly. So the DM file is still the same, but it's already set. And here is the original file, which has to be processed. The output pixel size, 0.1 meter. I think that's 10 centimeters. I think that's fine for this first order calculation. And I'm using usually fast nearest bilinear because this is a good compromise between geometric accuracy and spectral accuracy. If it's about geometric accuracy only, you could also use bilinear interpolation. So I'm defining the output. I'm gonna define this at a different location here for this in this sample directory, and give it a name. sample 1. Okay, maybe .bsq, that's a geometric corrector, so you can also change it in this field, and it will use this the name here. So let's process this. Let's see, I think this should work all right. May take some time, but it's not too slow, so you can wait for that. And it will only process 3 bands now, so it will be a rectified, geo-rectified RGB image. The IGM is the image geometry map, and also the scan angle file has been created. We can have a look at the result, which has been created. This one, scale image, scale zoom, so we have to show if there is some useful data. Scale zoom, here is the data. So the background is set to 65,000. That was the 40th Headwall data, and the image itself is in between. Okay, see, looks reasonable, but it's not highest accuracy yet. So we want to go for boresighting as a next step. So for the boresighting, we will have to go for a second data set. So we'll have to select a second data set which is perpendicular to the first one. Usually one would take a data set which has some buildings, some good spatial structures, such that the boresighting can be done correctly. I already prepared such a boresighting example, so we'll go directly into that to show you how it looks like. So it's the cross boresighting what I'm doing here. So if you have 2 crossing images, you could also do the boresighting against orthophoto. So the orthophoto could be done with auto GCP detection, so it will search automatically in the orthophoto for ground control points and do the boresighting that way. I'm doing the cross boresighting now, and I have the input file. Maybe I'm gonna restore a status I did before with all the boresighting done already. Boresighting, first one. This one was the status before the boresighting had been applied, and now I can go into the cross boresighting again. So this was the first image of this status, and you already see the ground control points appearing. And then I can show you the second one. That's the these are the 2 line numbers. You see the 4352 and the 30,680, whatever. I'm also selecting the cross boresighting status. That's this one, such that it's consistent. It would be required later for the parameters if you run the process. I'm also showing the RGB. So you have the second line, and you see they are cross against each other. Maybe usually you would arrange it this way around, such that the zoom windows are against each other on either side. So these are the corresponding GCPs now between the 2 lines. So I could, for instance, add one more. To add one more, I would click here in one side, push position, and here the same on this side, push position. And finally in the cross boresighting panel, I would say get and add points. And so it will, now I have 1 point more, I have 21 points, and this point will appear in the panel then. So it's point 21 now. So that's how you search for corresponding ground control points between 2 cross-referencing points. Finally, you would run the whole thing and do the cross boresighting, and maybe I could do that. So it will yes, it will go through all the points and search the optimum corresponding cross boresight values. So they're already given down here. And if once they are made, this cross boresighting, the ground control points have shifted or have coordinated coordinates, so they agree to each other, and you can save this status, as a boresight status. Maybe I would call it boresight 2 this time because it's a second trial, and so this is what you need later for the processing. So this is shortly shown how do you do the boresighting between two crossing lines. Okay, and now I can, if a boresighting is done, I can go into the full directory processing. So before I have been importing one image at once, but usually you would like to process whole campaigns. So for Headwall, you can choose in processor batch Hyperspecs, Nano directory processor. That's this one. And now you see you select the directory and no longer the so I would take the whole directory as an input, and it will found 37 files in there, 37 Headwall input files. I could select the number of bands. Usually you would do all of them. The field of view is still the same. And here, as before, it was the Hyperspec with the Applanix in your case, in the case of this data set, or it could be one of the other standards for Headwall, if no Applanix IMU is available. The DSM is still the same. That's one digital elevation model for all files, and I have to select the boresighting file now, which has been created before. So that's in here, the boresight. Maybe I take boresight 2, and here you don't have to add any more offsets. So that's just if there is a problem with the Headwall calibration, you could add systematic offsets for X, Y, Z. For the set coordinates, for the set coordinates only. UTM is default. Pixel size, I can do a guess of the pixel size. It's guessing about 2 centimeter pixel size, so 10 centimeters may have been a little bit too much before. And now I can processing. I don't use those. Maybe I want to do a JPEG preview for each image, and I want to do some mosaicing in the end, and I could create define the output directory. So this would be maybe that one, but I'm using now output 3 because it's a new one, and I could maybe check the consistency. So it seems to be okay, and now I could process the whole directory. This will take quite a long time. That's why I don't start it now, but you can have a look at the result now. So if I'm looking at the result, I can always use display image for results. You see the results in here in output 2. And there was the mosaic done in the end of all these processed files. So you have the geo is the processed image, the IGM is the image geometry map containing the coordinates for each pixel, and the map is the transformation map from raw geometry to rectified geometry. It's the same, or almost the same as a GLT file in Envy. So these are the 3 main outputs of rectification process. And so finally it makes a mosaic, and the mosaic looks like that. So in this case it's only an RGB processing, and you see that the mosaic fits very well of all these data sets, and you have a nice overview of the area. Okay, this was in short what you can do with PARGE and Headwall Hyperspec. Maybe some more details can be given upon your request or inquiry or support request. Thank you very much, and hear you later.